Hello and welcome to my Test 1 extra credit video. The format that I'm going to be doing this is I wrote all the problems down for Chapter 11, and I'm going to be going along and just kind of walking you through the process and demonstrating how I got to the answer using this pen and just demonstration. And I have the questions, I'll be reading them off of my computer. Question 38 from Chapter 11 was an aqueous solution of antifreeze is 40% ethylene glycol, C2H6O2, by mass. The density of the solution is 1.05 grams per centimeters cubed. Calculate the molarity, and the mole fraction of ethylene glycol. Okay, so what we have here is our information written down. It's 40% ethylene, the solution is 40% ethylene, which is 40 grams, because if the solution is 100%, then 60% of it will be the solvent, H2O, therefore making it 60% and 60 grams each. And I have the solvent, and solution written down here as we do in class, with ethylene, H2O, and the solution written down each individually, with their given values. And we use this for molality, this here, which is moles. It's defined as moles of solute over kilograms of solvent. And here below I have solved it out. The number of moles solute, we have to figure out the moles first for up here. So this comes from here. We start with our given 40 grams of ethylene multiplied by their molar mass, which you can calculate on your own using the periodic table very easily, or Google it, over 1 mole over that to get it in 2 moles, and this is our answer here for how many moles ethylene is. And then you take those moles and you plug them back in here. And you can calculate from your given 60 grams of H2O the kilograms by dividing by 1,000. Because grams, there are 1,000 kilograms in 1 gram. So that's how you get this number down here. And you plug in this value to the top of our formula, and this is your number of molality. Easy peasy. Molarity, you have to take this calculated moles for ethylene and use the volume of the solution in liters, specifically liters, and volume is mass over density. We weren't really given mass over density, but we estimated that 100 grams total from our percentages, and they did actually give us, it was 1.06 grams per milliliter. And all you have to do is some basic math with your calculator. You get 94.34 milliliters, and then you turn that into liters. Again, there's 1,000 milliliters in 1 liter, so you just do basic math for that. And your molarity, you plug all this back in, this here at the bottom, and your previously calculated 0.6444 moles of ethylene at the top. Divide, and you get 6.83 molarity. And your mole fraction, the very last part of problem 38. You have your H2O moles, because we already calculated how many moles ethylene was. That's this 0.6444 moles up here. Now we need to calculate how many moles of H2O are in this problem. So you take your 60 grams divided by the molecular weight, and that gives you 3.329 moles of H2O. And your total moles equal this. You plug them in and add them together, and this is what you get at the end, 3.974 moles total. And this number, you take them, once again, you divide them by the total. Because we're looking for the total number of the percentage of ethylene in this, you put ethylene on the top. See here? This is ethylene. So the fractional percentage of ethylene in here divided by the total. and that gives you the percentage of ethylene in this problem. There it is. Alright, now we're going to discuss problem 63, and I'll read it first. Pentane, C5H12, and hexane, C6H14, form an ideal solution. At 25 degrees C, the vapor pressures of pentane and hexane are 511, and 150 torr respectively. A solution is prepared by mixing 25 milliliters of pentane density given with 45 milliliters of hexane with the density given. A asks, what is the vapor pressure of the resulting solution? And A is this upper section here. What is the vapor pressure of the resulting solution? So first, we're going to write down all our given information at the top here. And as this is an ideal solution, there's neither of them dissolve into anything else. So there's no solvent or solute. So they're both just themselves. And I have all the information written up here, and because this is too volatile, they're both solute. Anyway, I mentioned that. So our mole fraction up here, we just did this mole fraction, which is the percentage of moles defined by number of moles solute over total moles. So, or not solute, but like a specific one. We take our given 25 milliliters, we're trying to find pentane first. Given 25 milliliters, turn it into liters, multiply it by the given grams per mole, turn it into moles. This here is our first calculated number, and it's the molecular weight of pentane. And that gives us 2.18 e to the -4th moles of pentane. We're going to leave that alone for a minute and calculate the moles of hexane by the same process. 45 is a given. This is a given here. This is our next calculated number. Once again, the molar weight. And we end up with 3.45 10 to the -4th moles of hexane. Now those two numbers, once again, we've done this before, you add them together here to give you your total moles of your solution. And that would be 5.63 10 to the -4th moles. And then you take it, you divide them, and when you get your division pieces, you plug them in to your vapor pressure solution here, or formula here, which is moles solute, and again, these are not solutes, but we'll use the term anyway, times the given pressure. We're given pressures. This is given pressure 1, and then given pressure 2, and this is Raoult's law. Ta-da! And then you plug in your numbers here from your calculations up here. Well, not that one, but these calculations here. You add them, and you're given, what's it called? Pressures. They gave you pressures here. You plug them down here, and that ends up as 290 torr. Ta-da! They give them to you in torr, you end up in torr. And so that's A. A is solved. Part B is, what is the composition by mole fraction of pentane in the vapor that is in equilibrium with the solution? Now, this whole time we were assuming that this was in equilibrium. It wasn't otherwise stated, so assume equilibrium. And we have our composition. We know how to get a mole fraction, which is moles of pentane is going to equal your fraction over the total. So here's our total. Here's our fraction, which I just took from here. And it gives us 0.69. And this does not have a, what's it called? Unit. No unit. Because torr times no unit cancels. Well, this becomes no unit here. So, That's problem 63. Alright, problem 67. Which of the following will have the lowest total vapor pressure at 25 degrees Celsius? A. Pure water, a vapor pressure that equals 23.8 torr at 25 degrees C. B. A solution of glucose in water with moles of glucose equaling 0.01. C. A solution of sodium chloride in water with moles of NaCl equaling 0.01. Or D. A solution of methanol in water with moles of methanol equaling 0.2. Consider the vapor pressure of both methanol at 143 torr and water. Oh, I'm sorry, I've been focusing on 81. So I've written each one down, and I will admit to a bit of confusion on this problem on my part, because I assumed we would be using this formula here, which is, oh goodness, why can't I think of the name of the thing? It's the Raoult's law, again, I think, which is pressure of solution equals the mole fraction of solvent times P of solution. Yeah, I think. Which is what I thought we were gonna end up doing, but you can't find the mole fraction of these, I think, without knowing any of the weights or fractions. You can't know the fractions. We don't know the percentages of any of these compounds, these solutions, so we can't determine the mole fraction. So you can, however, use your intermolecular forces, which would mean generally writing Lewis structures, but before we do that, there are some other ways to determine it. And I'm going to go with hydrogen bonding as number 1, because we're given the names of each of these. So, glucose. Here's a hydrogen bond, O and H. That means there has to be LDF, dispersion, dipole, dipole, and hydrogen bonding. Pure water. Not much to say on this. I think we all know the Lewis structure, at least, if not the molecular geometry of this being as such, and it's polar, which you would know if you drew the, if you drew the molecular geometry. And that means it has LDF. All of them have LDF. It's polar, so it's dipole. And it's a hydrogen bond. It's got hydrogen bonding. I apologize. Okay. But we also know how much it is. So we're going to continue on. This one, NaCl, strong, right? These both were strong. This one less so because it's a carbohydrate. NaCl, LDF, dipole, no hydrogen bonding. But we're looking for lowest vapor pressure. And the lowest vapor pressure correlates with the one that has 1, the most weight, and 2, the strongest bonds. And though these have hydrogen bonding, and we're just going to make the assumption we know that the last one has hydrogen bonding as well, that means C or A are our biggest contenders. So we're going to look at these more specifically. This is where you would draw your Lewis structure for each and compare, but we already know that this number is important here. And it's 143 torr on its own, methanol that is, which makes it much larger than pure water. And pure water has a something, this, whatever that stands for, I can't remember, of 1, because it's a non-electrolyte. So that's important too. And that's how we know it is C. And we're going to go real fast on this one. Calculate the freezing point and boiling point of each of the following solutions. Assume complete... this is 80. I'm sorry. We're looking at 81. I was reading 87. An aqueous solution of 10 grams of catalase, an enzyme found in the liver, has a volume of 1 liter at 27 degrees Celsius. The solution's osmotic pressure is at 27 degrees is found to be 0.745 torr. Calculate the molar mass of catalase. Molar mass is a very basic concept, and all that's different about this problem is the osmotic pressure and the effect that it's going to have on our formula, which is this. And R is our given value, T is our temperature in Kelvin specifically. Okay, R is this number here, you're given with the units, liters times ATM over K over mole times mole, and our pressure we are given. So we're going to end up shifting some things around so that we can find the M, which is what we're looking for, because it asked to find the molar mass. Duh. So you basically just plug in all of your things. You plug everything in, make it nice and neat. You calculate this from Celsius to Kelvin, easy peasy. You cancel out your units, you shift it over, you put this on top, this goes here, and it's an ATM. Kelvins get canceled out using this. Yeah, cancel. You end up with ATM, and this, your 7.5 torr, also ends up in here because you moved it over to multiply with it. So in order to get M alone on this side, you end up with all of those numbers and this at the bottom. Good job. And then you just divide. Simple. Oh, actually, no, I was right. Anyway, you end up with this at the bottom, and your final molarity is 39.818 times 10 to the negative 6 moles per liter of catalase. And then that's not it. You're not finding moles. You're finding molar mass. So moles is equal to mass times volume. So you can go in here and plug your numbers back in for 1 liter, and you use what you just calculated, your moles times 1 liter, which is this number again. I just didn't have space to write it out. Moles of that, so you can calculate it, moles per liter or whatever. And then your molar mass is mass of your solution, defined as mass of the solution, over moles of your solute. So 10 gram solution, that was our given in the problem, over this calculated number right there, equals 2.51 times e to the negative 5th grams per mole. Thank you. I hope I did a good explanation.